Today, we want to continue talking about integration. Not technique, but thinking behind integration. So what we talked about before, we're going to talk about it again. Then we're going to do more process, and then we're going to do more integration is multiplication, but one of the factors is continuously variable. This means that integration is just addition. But integration is multiplication, but one of the factors is continuously variable. Let's think about addition and multiplication and how they're related. When we do addition and all the terms are the same, we get to multiply. It's like, oh, it's a bunch of fives that we're adding together. That's just 3 fives. We get to use multiplication. It's like an upgrade. It's like, oh, look at all this stuff. Everything's the same. We get to multiply. Area is equal to length times width. If the length is constant throughout the entire width, we get to multiply. In between, we have a discrete sum, 5 plus 6 plus 7. Here, we're doing addition, but the terms are not the same. So there's no multiplication available. We don't get to do multiplication. But what we have is a discrete sum. Because there's a 5, there's 3 terms. There's a 5, there's a 6, there's a 7. We're just adding up those 3 terms. Up from that is the so if we're doing length times width in a discrete sum, we could do this one length times width, then we do the next length times width, then we do the third length times width, and then we would just add those up together. So in a discrete sum, when everything's super pixelated, we just calculate our multiplication for each of those little rectangles and then add them up at the end. Integration is one step further because now, instead of changing in a discrete amount, first 5, then 6, then 7, things are changing continuously. And we want to do things like add up all the values of f of x from a to b. But a and b represents an interval of real numbers. And there is no next real number. So we had a discrete sum, 5, then next is 6, then the next is 7. That's a discrete sum. There's a next integer. But when we're talking about real numbers, there is no next real number. Our strategy is based on backing up to the previous problem, making f of x constant for some small change in x. So we just back the continuous problem up to the previous problem. We get to multiply if the length is constant for some small change in the width. So we say, let's just make the length constant, f evaluated at this particular value of x, and multiply by the width of the interval. We get to use length times width. Then we're creating a discrete sum. I goes from 1 to n, the first, second, third, fourth, all the way up to the nth rectangle. And then we do the calculus thing. The calculus thing is, let's use an infinite number of rectangles that are infinitely thin. That's the thinking behind integration. Is it going to help you when we have to start doing trigonometric substitution? Probably not, because that's when we're thinking mechanically about pushing some symbols around a page. But running in the background of all of our integration problems is this idea. Integration is multiplication, but one of the factors is continuously variable. And so in that regard, integration is just addition. I mean, here's integration and here's addition, just like right on the other side, and there's an equal sign in between. So we start with area, and actually we tend to start with area and distance is equal to rate times time. All of your integration problems, everything that comes up with applications of integration, it's all just going to be multiplication. Anytime you find multiplication, that's a potential integration problem. Length times width. If the length area is equal to length times width. If the length is constant, if the length is constant, then we get to multiply. If the length is constant, that allows us to multiply length times width. Notice that every place along the width I pick, the length is always the same. That's where the length is constant. No matter what value of W I pick, no matter where along W I pick, the length is always the same. Here, the length is continuously variable. Every place I pick along what I would want to try to label as the width, every place I pick down here, I have a different value for the length. The length is different along at every value between A and B for the width. So we switch to integration. We start first by imagining this is just a bunch of rectangles, and then we just use an infinite number of rectangles. And so the area is the integral from A to B of the length dx. Notice that the width still shows up. That's all the values of x that we're plugging in. We're plugging in from A to B. So in this first round of problems, all the area problems were always length times width. And the game was about coming up with an expression for the length in terms of some delta variable that serves as the width. So here is one of the problems that we had. Any questions before we do a problem? I don't always have Stargate artifacts in my lectures, but when I do. So we look at this. One of the areas that we had to calculate was a circle. Now, the point of calculating the area of a circle using calculus techniques is not so that we can find the area of a circle. We already know a formula for the area of a circle. We know the shortcut. for how this works. Let's suppose that we have a circle of radius C. Mark the radius down here. Oh, I missed. Try to hit that point. I don't want it labeled R. I'll use R as a variable. So we know that the area of the circle is 5 squared times pi. That's not the point. We're going to do calculus on it. We're going to imagine this as an infinite stack of rectangles that are infinitely thin. So what we're going to use for area is length times width. What I'm going to do is I'm going to draw a typical rectangle. So this example is a circle is a stack of rectangles. A circle is a stack of rectangles. So I'm going to draw a typical rectangle. I will also refer to this typical rectangle as a slice of the circle. So the circle is just a stack of rectangles. So that rectangle there has a length and a width. Now, I'm going to put the width down here or up here. And it's the length that we're going to make smaller. If you don't like calling this short side the length that goes up and down, you can call it the height. I'm going to take the height of this rectangle, and that's the one that's going to get thinner to make my infinite stack of rectangles. So that I'm going to refer to as the delta variable. The delta variable is the one that gets thinner to make the infinite stack. So our delta variable is going up and down. So the delta variable is the one that's getting thinner to make your infinite stack. So that's the delta variable is the dimension that has to get infinitely thin to make our infinite stack. So now I'm going to write down the area of this slice. It's just the width times delta x. Where delta x is the height. Now we're grounded. We have something that we're going for. We've established what direction our variable is going to go. I've identified what's getting thinner to make my infinite stack. That's my delta variable. That tells me that x is going to be an up and down variable. I just have to decide where to put the x. There are only a few places that make sense of where to start x. One end is the slice, the other end is 0. The only reasonable places to start x are at the top of this circle, the middle of the circle, or the bottom of the circle. Two of those are pretty much the same. So we can either start at the middle and go up to the slice, or we can start at the bottom and go up to the slice. Remember, once we decide where we're putting the variable, we're deciding where 0 is going to be, and we're deciding which direction is positive. Because the end is the slice, 0 will be at the other end where we put our variable. I have to decide where I got to put the variable. I'm going to choose for you. So I'm choosing 40. So on one hand, you should be like, oh, hey man, you can't tell me what to do. Then I'll be like, oh, well, let's make a choice. And I go, nah, you got this. Go ahead and make your choice. That's what I was going to do in the first place. And you're like, the first way you said it was an affront to my freedoms. We can literally put x wherever we want, but there are only really 3 places that make sense. I could put the x 10 pi times e squared units below the bottom of the circle. But why? Why would we do that? And all the programmers are like, well, so that no one can decipher your code, so that you're still essential to the company. So x is going to be the distance from this the center of the circle up to the slice. X is going to be the distance from the center of the circle to the slice. One end is the slice, the other end is 0. So once I decide that x is the distance from the middle of the circle to the slice, we establish where x is equal to 0. So that means that x is equal to 0 here at the center of the circle. Furthermore, we put the slice in the positive direction. So up is positive. And that means that the top of the circle happens when x is equal to 5, since the radius of the circle is 5. The other reason that I wanted to put x equals 0 at the middle of the circle is that down at the bottom of the circle, x will be negative 5. Is everybody okay? Now what I need to do is write w in terms of x. Now that I've got x defined, I need to write w in terms of x. Now, what comes next is not a method. What comes next is what we're going to do in this instance. So at this point, we just have to start making stuff up. We have to start figuring things out. This is the part of the math problem where we actually have to do math. So a lot of times in algebra class, you hear students say things like, well, I'm fine once the problem is set up, but that I have trouble setting up the problem. Setting up the problem is the problem. That's the whole point. Understanding what you're trying to do and how to translate those ideas into math that you can hammer on with your rules of algebra. That's the point. That's the job. Actually hammering out the details, that's something that we want to mechanize as much as possible. That's why we have that FNINT on our calculator. We don't want to have to calculate integrals by hand. But we need to be able to set up integrals that will give us the quantities that we want. Does that make sense? So when you find yourself saying, I don't like word problems because they're hard to set up, that's just because math is hard. We're trying to take the things that we observe and quantify them in such a manner that we can work with them. and use them to describe the world and make predictions about what could happen next. So this is the thing that's happening. Now, I'm going to give you this one for free. This is just someone said, well, it's a circle. I need a relationship between this W way up here and this vertical value down here. And what we know is that the distance from the center of the circle out to any point on the circle is always the same. So what we're going to grab for this particular problem is a right triangle where one leg of the right triangle is X. The other leg is going to be, well, half of W, and the hypotenuse is 5. That's the big deal. That hypotenuse in this right triangle is always 5. That gives us a relationship between this vertical quantity X and this horizontal quantity W. Well, half of W, because the other leg of that triangle is half of W. So I get a relationship between X and W. I can say X squared plus half of W squared is equal to 5 squared. And what we want, there's just a lot of glare there. What we want is to write W as a function of X, ideally a function of X. But at least now we got a relationship between W and X, and we can turn this into a function. So we can solve this for W and say that W is 2 times the square root of 25 minus X squared. This is actually just path solving for W, but I know that the width should be a positive quantity, so I don't care about the plus or minus. I only care about the plus. Now I've got W in terms of X, so I can say that the area of that slice is my width, which is going to be 2 square roots of 25 minus X squared, times the height, which is our ever thinning delta X. Question? This is the area of one slice. And what we have is, depending on the value of X, when X is 0, then our width is 20, square root of 25 is 5 times 2 is 10, then the width is 10. When X goes up to 5, I have 25 minus 5 squared, so that's going to be 0. And that makes sense because at the top, there's no width anymore. Also, at the bottom, when X is -5, 25 minus a -5 squared is also 0. So our width is 0 down here at the bottom as well. The problems that we did last time, we had linear functions because we looked at the width and the sides were just a triangle. So things were changing linearly, but now things are changing as a circle. So it's going to be the square root of X squared function. In a Riemann sum, we would add up all these rectangles and then let the number of rectangles go to infinity. But since we're sophisticated modern calculus students, we know that Riemann sum is just going to turn into a definite integral. So for the total area, I'm going to write a definite integral. There's a factor of 2. I always like to pull my constant factors out, and I just integrate the function. The delta X the discrete delta x should become a continuous dx as the delta x gets infinitely thin to make our infinite stack of rectangles. What we need to do now is this calculation, root 25 minus x squared times dx, for all the values of x where we have a rectangle. The rectangles start down here at the bottom of the circle when x is -5, and they continue all the way up to x equals 5. That's where the circle starts and stops in terms of x. So we'll integrate from -5 to 5. Unfortunately for our heroes, this is a type of integral that we haven't learned how to do yet. This is a trigonometric substitution, but we still have ways of integrating things. So I just want 2 times the integral of square root of 25 minus x squared, close the radical with respect to x from -5 to 5. Close the command. I don't care about mode. 78.53. This should be some multiple of pi. Looks like about 3 times 5 squared. If I divide out the pi, there's my 25. I know there's a 0.00, a bunch of 2, there's a 28 out there. This is your calculator saying, no, 25. So we get an area of 25 pi, just as we had foreseen. A lot of times when I ask you to do these problems, I say round your answer to 5 significant figures. So we'll go with 78.540. Also notice that even though 25 pi is only approximately 78.540, I just put an equal sign in between. I cannot train myself to use the squiggly equal sign for approximately equal to. So we're just going to have to understand that this is approximation. Any questions? And honestly, if someone comes along and they're like, well, I see that you've used an equal sign, but 25 pi is an irrational number, and thus its decimal representation goes on forever and never repeating and never terminating like you've terminated here. To which the response is, dude, you know what I was talking about. So if that's your only complaint, then we're going to assume that things are all clear. You know what I mean? It's like when a kid says, can I go to the bathroom? And the teacher's like, oh, I don't know, can you? The proper response is not like, oh, may I? That's like the one the teacher wants. Never do what the teacher wants. Just get up and say, let's find out, and walk the heck out the door. So, because ultimately, the teacher is being a dick in that situation because the teacher knew what you meant and you phrased it properly. And you even asked. You know what I mean? It goes back to behavior modification. Set up systems that encourage the behavior that you want. So if the student has enough respect to say, can I go to the bathroom? Yes. Say yes. They even ask. If you don't want that kind of behavior, the kid will say, well, I don't want this interaction with the teacher, but I do need to go to the bathroom. So I'm just going to get up and go. Which is, by the way, what you do in this class. You don't want to go. I guess what I'm saying is I don't like forcing children by telling them what the rules of society are. Because the more I tell them how we work in polite society, when they watch us not do that, they start getting the idea that the rules don't apply to these adults. Then they start getting the idea that when I'm an adult, the rules won't apply to me. And I get to tell people what to do. So now, messes everything up. Primary source concern. Just model the behavior that you want. So this was an excessive amount of math to throw at the area of a circle. Let's modify it a little bit. Let's suppose that we're tired of this circle always rolling around and like a little breeze comes along and it rolls off the table. Let's suppose that we truncate 1 unit from the bottom of the circle so it'll stop rolling around. Let's suppose that from this circle with a radius of 5, let's suppose that we truncate 1 unit from the bottom of the circle. Now our circle will stop rolling around. And let's suppose that we want to find the area of this truncated circle. In the setup, I would still have a rectangular slice. Delta X is still this height. That's what's going to have to get thinner to make an infinite stack of these rectangles. I can use the same value of X that establishes the same X equals 0. And we're going to use the same right triangle to get a relationship between X and W. This triangle still has legs of X and W over 2, so I can still write that W is 2 square roots of 25 minus X squared. So the area of my slice hasn't changed. I still want W times delta X. And my width is still 2 square roots 25 minus X squared. What has changed is the values of X that I'm going to plug into my integral. Plug into that I'm going to integrate over the endpoints of my interval. I'm still going to have this 2, and I'm still going to integrate the square root of 25 minus X squared. Delta X still becomes dx. But now notice that the bottom of the circle is not at -5 anymore. I've cut 1 unit off the bottom of the circle. So down here at the bottom, is where x equals -4, because at the bottom of the circle is where x equals -5. I've cut that part off. So now x starts at -4. I still want to go all the way to the top of the circle. But instead of going from -5 to 5, I'll go from -4 to 5. And that will leave 1 unit truncated from the bottom of the circle. So I can actually just reuse the same integral and change the -5 to -4. And we get 74.452. It's going to be an easy multiple of pi? No. Questions? Look how limited you were with your stupid pi r squared. All I have to do is flatten the circle a little bit, and all of a sudden there is no more pi r squared. What's the general formula for a truncated circle? I don't know, you don't have one. I didn't change the shape of the circle. It's still a circle of radius 5. There's just a piece cut off the bottom of it. I can't just say this is a circle of radius 4 now. It's still 5 up to the top. Any questions? So we get lots of extra cool stuff just by truncating this. So if I change this to, if I want a semicircle, the area total I could just integrate from 0 to 5, and that'll just give me the top half of the circle. And there's my 12.5 pi. Questions? This right triangle thing only works in this case for the circle because the hypotenuse is always 5. No matter how we distribute the lengths of x and w, or half of w, that hypotenuse is always 5. If we're in a situation where that hypotenuse of the triangle is not always going to be the same, then we don't get to use this. I have a relationship between 3 things: the x, half of w, and the hypotenuse. So I'm going to need some other information to combine those variables. We're going to upgrade this by 1 dimension. And we're going to tomorrow talk about volume. Right, volume. We're going to talk about volume as cross-sectional area times height. This is something that we do already. We already think of volume as cross-sectional area multiplied by height. If I have a rectangular solid, oops, There go the bells. I don't know why I had to draw a rectangle saw. Just like, right, volume is length times width times height. The length times width, that's the cross-sectional area. Also, if you have a volume of a cylinder, it's going to be pi r squared times the height. Pi r squared is the area of the circle, and the height is the length through which that circle is projected. So here's our cross-sectional area multiplied by the height. Here's the cross-sectional area multiplied by the height. If we have a rectangular solid or a cylinder, then that area will always have the same value, so we get to multiply. If that area changes, though, we're going to have to integrate. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.